looking forward to talking a little bit about what seismologists do, what seismologists like me, so-called global seismologists do. When you think of seismologists, you probably think, well, seismology is interested in earthquakes, in studying earthquakes, why they happen, how they happen, how often, where, and when. But in fact, earthquakes can be used also for other purposes, for purposes of investigating the deep structure of the Earth. And I thought the recent Sumatra earthquake of last December, which of course has been a great disaster for the populations
around the Indian Ocean, I thought this was a good example to sort of thread in to show a little bit about how seismologists can use and interpret seismic data. So let's talk a little bit about the Sumatra earthquake. As you know, this was the largest earthquake in 40 years. It was huge, and it had a huge impact because, primarily because of the associated tsunami. It was not the first earthquake in the last 100 years that had, as a consequence, large tsunamis. There were a series of very large earthquakes in the 1960s, such as, for example, the Alaska earthquake of 1964, which was slightly smaller than what we think the Sumatra earthquake was, which created a lot of damage, for which the tsunami created a lot of damage in the region around Alaska. Hawaii has been hit by large earthquakes and large tsunamis related to large earthquakes many times. In the 1940s to the 1960s, at least 4 such earthquakes struck, and each time, and in 1946 in particular, the island of Hilo was struck by the tsunami corresponding to an earthquake in the Aleutian Islands. Not such a great earthquake as the Sumatra, but still pretty significant. And after this earthquake, the Tsunami Warning Center was created, and also this particular area of the big island in Hawaii was made into a park. Now, the Sumatra earthquake is really giant in many respects. It ruptured a very, very long stretch of a plate boundary here in the Indian Ocean, over 1,300 kilometers. What we see here, all these dots are the locations as obtained by seismologists looking at a global network of stations corresponding to the aftershocks of this earthquake. From just looking at these locations, we can see that the rupture, which started somewhere in the south, propagated a long distance towards the north. 1,300 kilometers of rupture zone. The slip corresponding to the motion, the displacement between the two faces of the fault was about 15 to 20 meters. And the shaking lasted 8 minutes, which you can compare. Perhaps some of you have felt the Loma Prieta earthquake. That shaking lasted only about 20 seconds. So you can see that would be like 500 seconds, more than 20 times longer duration. Just that gives you a sense of the size of this earthquake. Of course, the effects, as I previously mentioned, were huge, primarily because of the tsunami. Here is a picture of the one particular shoreline in Thailand before and after the earthquake, with the waves penetrating quite deep inland. Another view showing how high the tsunami wave reached, 10 to 20 meters, in some places in the vicinity of the earthquake. Now, this earthquake is unusual if we compare it to the statistics of worldwide earthquakes. Over the last 100 years, say, we expect magnitude 9 and larger events to occur rather infrequently. The expected occurrence is about once per decade. The larger the earthquake, you can multiply by 10
the number of earthquakes as you go down in magnitude by 1 unit in general. But the actual number in the last 100 years has actually been smaller. It's more been like 1 every 20 years. So in the long term, things equalize, but in the short term, the occurrence of the very huge earthquakes is not completely regular. And in fact, there was a cluster of large earthquakes in the 1960s around the Northwest Pacific. Not quite, some of them magnitude 9, some of them a little bit less, and then nothing for the last 40 years. So this earthquake compares, its magnitude has recently been revised. At first it was announced as a magnitude 9. We now know that it was actually larger, 9.3, and so it's the second largest earthquake in the last century, the largest one being a Chile earthquake of 1960, which ruptured a length of about 900 kilometers along the coast in Chile. And the Alaska earthquake has been degraded now as the third largest earthquake in the last century. In terms of the activity in the last 20 years, if we plot it as a function of a measure of energy, which is the so-called seismic moment release, actually in the last 30 years, you can see that there are earthquakes of large size, maybe magnitude 7s or 8s, occasionally around the world. Some, they don't occur very regularly. Some of them occur in bursts. Some of them are separated by longer quiet times. The Sumatra earthquake in itself really accounted for an energy release which would be equivalent to 5 to 6 more sort of regular frequent earthquakes. If we look at the distribution of very large earthquakes, magnitude 8 and larger in the last 15 years, we see, as expected, and as you will see, that they all occurred around the Pacific Ocean. And so this leads to looking at the geophysical context of this earthquake. The theory of plate tectonics has been established quite firmly in the 1960s, and we now know that the top of the Earth is covered with so-called tectonic plates, whose thickness is on average about 80 to 100 kilometers, and which move with respect to each other. And the motions are due to very slow convective motions in the Earth's mantle. The Earth has a solid mantle and a liquid core, outer core. The solid mantle, however, on geological timescales, moves like very viscous fluid, with the rate being expressed at the surface by the rate of motion of the plates, which is on the order of a few centimeters per year. If you look at the different plates coverage of the Earth, there is about 20 large plates which interact with each other at their boundaries. We are sitting here on the North American plate, and California, in fact, is on the boundary between the North American plate and the very large Pacific plate, which rub against each other along the San Andreas Fault system. Other plates interact in different manners. Some of them separate from each other. That occurs in mid-ocean ridges. They converge along subduction zones. And this particular earthquake occurred here at the boundary between the so-called Indian-Australian plates and the Eurasian plate. This is a region of quite complex, where a number of microplates are present. The signature of plate tectonics, of course, is visible if you look at the ocean floors. You can see the huge mountain ridges in the middle of the oceans. These mountain ridges mark the boundary of plates which separate from each other, with the magma coming from the mantle and accreting to form the crust. And the new crust has to be consumed somewhere, because the volume of the Earth isn't increasing.
and it gets consumed in trenches. You can also see in the topography deep trenches, some of which reach 10,000 meters in some areas of South America and the Western Pacific Ocean primarily. The seismicity of the world tracks the boundaries of the plates. The earthquakes, most of earthquakes occur along the plate boundaries, both in the mid-ocean ridge system and also along the subduction zones. Here in this plot you see that the magnitude of the earthquake is indicated by the larger the earthquake, the larger the circle, and you can very clearly see that the largest earthquakes occur around the Pacific Ocean. So from that point of view, it's not surprising that if we have had the Sumatra earthquake where it happened, it would have happened around this system. Of course, this is not exactly the Pacific Ocean, but it's part of this large system which is dominated by subduction zones, by zones where two plates meet and one has a tendency to go under the other. This is just a sort of zoom on the regional zoom on what is going on in the Indian Ocean region. India is moving northward, and as it moves northward and collides with Eurasia, it builds the Himalayan mountains, and in the back of the Himalayan mountains lifts up the Tibet Plateau, which is the highest plateau in the world with an average elevation of 4,000 meters. And as it moves like an indenter into the Eurasia, the crust, the material of the plates here in Eurasia has a tendency to be extruded towards the east and then interact with these arcs here, which mark the boundaries of the plates, where the oceanic plate in general dives under the continental plate. And again, this is the location of the initiation of the Sumatra earthquake. So what happens in this kind of setting where the Sumatra earthquake occurs is that you have this oceanic plate diving under the other plate, generally the continental plate, and along this boundary the motion isn't smooth. It actually stops and goes, stops and goes. While it's stopped, stresses accumulate, very high stresses accumulate, and at some point a very large area of this contact zone ruptures in a very large earthquake. In the particular case of the Sumatra earthquake, this was compounded by the fact that the area where the earthquake happened was under the ocean, and so the rupture started somewhere at depth and propagated upwards and also along the boundary and lifted up the seafloor here. As it lifts the seafloor, it lifts up the water, and this is the reason why these large subductions on earthquakes that are relatively shallow, that actually break the surface under the ocean, also are very often tsunami-genic. Just a word about tsunami. What happens in a tsunami is that the seafloor gets uplifted somewhere at some distance offshore by a rupture from an earthquake like the Sumatra earthquake, and starts a wave which propagates both inland and out to sea. While the wave is in the open sea, it's basically moving a block of water towards the shore. When it's out in the sea, this volume of water only creates a small, very long wavelength, 200 kilometers or longer wave, which then has to interact with the rising seafloor towards the shore. And as it moves towards the shore, it has less space to contain the motion in, and therefore it rises and creates this large protruding wave, which eventually breaks on the shore, and that's where the damage happened. These waves travel relatively slowly by seismological standards. They travel at the velocity of a jet, whereas seismic waves generated by the earthquake travel much faster. They travel at several kilometers per second. So in principle, you should be able to warn of an impending tsunami if you have a system involving different types of gauges, seismic gauges in particular, and also tide gauges. This has been, of course, since the Sumatra event, these issues have been discussed very widely, and some measures have been taken to develop such a system in the Indian Ocean. The Pacific Ocean already has a well-rounded tsunami warning system, and what happened in this particular case is that the communication did not quite, unfortunately, function between the high-tech capabilities of the Pacific Tsunami Warning Center and the chain of command that would have been necessary in the Indian Ocean to warn the populations. So the tsunami started by the uplift of the seafloor and then propagated rather slowly, reaching different coasts around the Indian Ocean, most of them several hours or many hours after the tsunami. But let's move to the seismological research context. This earthquake actually happened at a time where the seismologists are very well equipped. There has been an effort in the last 25 years to develop a network, a global network. It's an international effort, which now comprises over 200 stations all over the globe. These stations are equipped with very state-of-the-art seismometers, which measure very tiny motions generated by earthquakes at the other end of the world. And they also measure them in a very large bandwidth, capturing the whole seismic band, useful seismic band. They capture them faithfully and with a large dynamic range. So, and this network was really started being installed only in the 1980s, benefited from improvements in technology for the building of the sensors, and also digital recording, telemetry, and all these technological improvements that have been available in the last 20 years. And of course, when the Sumatra earthquake happened, this large network picked up the vibrations of this earthquake. And I'd like to talk a little bit about these observations. First of all, just a picture showing the hero of the seismic networks, which is a so-called very broadband seismometer called the STS-1 seismometer, which is installed in most of the stations of which I was showing in the previous slide, and is a unique instrument which actually was first built in the 1970s and is currently a problem because it's not manufactured anymore. It's really a family type business in Switzerland that's been manufacturing these instruments. They rely on a force feedback mechanism which allows a very precise following of the motion of very small motions of the boom. The principle is it's basically the principle of the pendulum, measuring the differential motion between the frame of the pendulum and the pendulum itself, which is suspended through a spring, where the mass is suspended through a spring. The view of the Sumatra earthquake can be very different in very different frequency bands. This is just a time series of several days of data filtered in different bandwidths at low frequency. Low frequency in seismology is, say, 100 seconds to 1 hour. The fundamental mode of vibration of the Earth is almost 1 hour, 54 minutes. And this is high frequency. High frequency is periods periods shorter than about 1 second. Usually you can pick up useful signals at large distances up to about 10 hertz frequencies. And you can see that just looking at this very generally speaking, there are very different types of information contained in these records. This is a narrow bandpass filter at low frequency showing bursts of energy which correspond to waves that have traveled along the surface of the Earth many times around the globe. In this one, what you pick up is mostly all the aftershocks of the earthquake. Many of them rather small, maybe magnitude 5s and 6 compared to the main shock. Typically, a seismologist cannot give a talk without showing at least one set of recordings. A typical 3-component recording of a large distance earthquake looks like this. Very typically, you see different types of energy arrivals. The first arrival called the primary wave, the secondary arrival, secondary wave. Primary wave is a longitudinal wave, elastic waves. The second one is a shear wave, so the polarization is different. You can see the signature differently on the different components. And then it's followed up by slower waves, lower frequency slower waves, which are traveling primarily along the surface of the Earth, called surface waves. All of these waves interact with the internal structure of the Earth, and some of them, as I mentioned, travel along the surface. Some of them travel into the Earth and interact with the discontinuities inside the Earth. This is how we know we have a liquid core, because of a shadow zone that is created by, if you put seismometers all along here, the surface of the Earth, and you follow a particular first arriving wave, a P wave, you will see that at distances larger than about 9,000 kilometers, there is a region where you don't see the P wave anymore because it gets refracted at larger distances into the core. For shear waves, actually you lose them because shear waves don't propagate in liquids, and that is the main evidence for the liquidity of the outer core. There is also a solid inner core, which has also been picked up by the careful analysis of waves traveling through the core and interacting with the boundary between the liquid and the solid inner core. But beyond these simple models of the Earth, of course, which have been built over, starting in the early years of the 20th century, when the first seismic instruments were made, started recording usable data, we have now gone much beyond this and have very good reference models of the radial structure of the Earth, which conveniently is made up of more or less concentric shells, spherical shells. However, there's a lot, of course, of other complications in the structure that is going on, and this is, of course, what is the most interesting from the point of view from currently learning about the dynamics. But let's go back to this more high-frequency observations of the Sumatra earthquake for a minute. This is a little bit of a busy slide, but this is just a recording of a P wave, which is the primary wave, the first wave that is observed and is easy to observe because it comes very strikingly out of the noise. And I'd like to just concentrate on this diagram, which shows different recordings of the P wave for the Sumatra earthquake, which was very, very long. It lasted 500 seconds, whereas for your run-of-the-mill earthquakes of magnitude 6 and 7, these waves usually last just 10, 20 seconds at most. But what you can see is here a sort of a record section showing recordings at many different stations in different directions around the source, so in different directions all around the world.
And what you can see is that the duration here of this energy corresponding to this first arriving wave actually changes with the azimuth, that is, with the direction in which you're looking. And this is one manifestation of the fact that this rupture ruptured in one specific direction, that it had what we call a directivity. Along the direction of the propagation of the rupture, it's like a Doppler effect. You see the P wave is shrunk, it's shorter, whereas broadside it is, whereas in opposite azimuths it will be much longer. So just looking at records without doing any sophisticated analysis or processing, there is already quite a lot you can say about this earthquake. Of course, there are many sophisticated developments that have been worked on in the last 20 years that now allow to back project data that are observed at a station somewhere around the world, back project that to the source, and obtain images of the rupture with detailed sort of time-space history of the rupture. So, for example, this is one model that was obtained very quickly, very shortly after the earthquake, showing first of all the extent of the rupture. With here, this is indicated the slip at every the maximum slip being sort of 1/3 of the way along the rupture, and also how this ruptured in time. If we look at the long period, low frequency end of the record, if we filter at low frequency, we see these bursts of energy, which correspond to these waves that travel from the source to the station, either in this direction, which we call the primary direction, or in the opposite direction along the long way. And each time the waves goes one time around the Earth, you get a burst of energy. So R1, R3, R5, R7 are going this way, and then R2, R4, R6, etc. are going this way. You notice that this is a record of about 12 hours. This is not for the Sumatra earthquake, but is another more standard earthquake of magnitude 6.8. Anytime you have an earthquake of magnitude larger than maybe 6.5, you can observe these waves. And of course, they attenuate with time. They attenuate with time for several reasons. One is just a simple geometrical spreading effect. The other one is the fact that the Earth is not completely elastic. It rings, but it also attenuates the motions with time. And that also gives us some information on its structure. For the Sumatra event, this record section was made from a selection of stations around the world, showing just the first 4 surface wave arrivals. And you can see, you can track them as a function of distance from the earthquake source here, from 0 to the antipode at 180 degrees. And you can see these different wave trains. You can follow them very nicely on this plot. The magnitude 9.3 earthquake is here. There was an aftershock of magnitude 7.1, which sort of gives you this additional shadow starting about 200 minutes after the first earthquake. From long periods, you can also learn about some, without doing much analysis, or much processing, you can learn about some characteristics of the rupture. And again, it's very strong directivity. What we compare here is at a station in Eurasia, which is located in that direction from the source. This is indicating north. We compare the low frequency record of the main shock with that of the aftershock, which was magnitude 8.7 in March, on March 28th, and which ruptured in the opposite direction. So the main shock ruptured towards the north, the aftershock ruptured towards the south. You can see that the records look completely different. It's not just the size of the earthquake, but it's also its character. This one, the station was located in the direction of the first arrival, so the first wave is very strong, whereas the second wave is much subdued. this would be like the second wave, the R2 coming this way. For the other earthquake, which ruptured to the south, on the other hand, you can see that the amplitude difference between those two wave trains are quite different, and this second wave train, which normally should be smaller than the first one because the distance traveled is longer, is actually larger than the first one, which gives you already a qualitative indication that the process of these two related earthquakes is quite different. Here's another example of the same, where of a station. This station is in the Pacific Ocean in this direction, and you can see again. This is time scale here is slightly different, but you can see that the first earthquake is in the back of the rupture, and so the first train is smaller than the second one, whereas for the second event, it's the opposite. So lots of fun games you can play. But the main, the very, very exciting part for seismologists about the Sumatra earthquake is the ability to form from these very long records, hours, several days, to form spectra, that is, go in the frequency domain and see the ringing of the Earth, the vibrations of the Earth. If you take standard processing, which is taking the Fourier transform of this long period record, into the frequency domain, you see appear a number of peaks. This is now in frequency. These are millihertz, and you see these peaks. These peaks are characteristics of the Earth's structure. It's basically the same as if you have a bell that's ringing. The tone of the bell depends very much on the shape of the bell, its size, and what it's made of. And so by analyzing, just hearing bells, you can already get an idea of how big the bell is, and if you have some additional knowledge, you can infer what it's made of and what its shape is. And so the same holds for the Earth. From looking at these peaks and comparing them to a reference Earth model that has been built over many years and now is quite stable, the differences in frequencies from the reference model can tell us about a lot about the fine structure of the Earth. And some of these modes are, all of these modes are well identified. For example, these big peaks are the peaks corresponding to what we call the fundamental mode of vibration, and some of these other peaks correspond to modes that have, these peaks are largely sensitive to the mantle structure, and some of the smaller peaks are also sensitive to structure in the core. The fundamental vibrations of the Earth, the very gravest modes, there's two types of them, modes that correspond to shear motion called toroidal modes. So the fundamental one is called 0T2 and correspond to this type of motion of one hemisphere with respect to the other. Then some higher modes correspond to more complicated differential motion between different parts of the Earth. And modes that correspond to the more compressional motion are the spheroidal modes, of which there are also several types. The most grave radio mode, which has a period of 20 minutes, which is called 0S0, which just corresponds to contraction and expansion of the whole Earth. And then modes that change the shape of the Earth, the gravest one being the 54-minute one, 0S2, which is called the football mode, or I guess. And you can see them in the spectrum. This is a spectrum of a record in Kenya of the Sumatra earthquake. So as a function of frequency here in millihertz, you see the gravest mode here, 0S2, the beach ball mode or the football mode, and then some of the other modes with this 0S0 being very clearly seen here. Now, why is this so exciting to us? This is exciting because generally we don't see these peaks that clearly. 0S2 is very faint on most earthquakes to date,
And in fact, to really study it, seismologists have had to stack many records from many stations in order to bring down the noise and be able to really analyze these modes. For the Sumatra event, they just stand out, they are there without any processing. And so one of the exciting things about these data is that they, for the first time, they provide an opportunity to verify a lot of theoretical knowledge that was so far only theoretical. So this is another example of a spectrum where, in fact, you see modes that you shouldn't be seeing. For example, this is a vertical component record. You shouldn't be seeing toroidal modes on the vertical component, but you actually pick them up, and that is an indication of coupling between the earthquake waves and the Earth rotation in particular. But it also is coupling due to complexities in the structure, such as anisotropic structure. What's even more exciting to a low-frequency seismologist is that the theory predicts that a mode like 0S2, which would be made of only one line if the Earth was only one-dimensional, that is, it was really concentric shells and no other heterogeneity in it, it would have one line. Rotation splits this line into 5 lines, and in addition to rotation, heterogeneity due to the dynamics of the Earth also splits the lines. And for this particular earthquake, you can see that we pick up on one record, this is in Australia, here we pick up 4 of the 5 lines of 0S2 and 3 of the lines of 0S3. But in some records, actually, if you process the records appropriately, you can see all the 5 lines of 0S2, and actually here I'm showing the 7 lines of the next mode, 0S3. There's 2L, this is L, and there's 2L plus 1 lines, so 2 times 3 plus 1, 7 singlets. So this is something, again, that has not been observed on single records ever before. Another interesting aspect of this is that if you compare the spectra, this is again this 0S2 5-line mode and this 0S3, the 7-line mode, at different stations around the world, you see these 5 peaks. They're excited at different levels depending on the location of the station with respect to the earthquake. And at this station here, this particular station, there is only one peak. Well, that's also something that's predicted by theory, because this is alert in the northern territories of Canada, and it's very close to the pole, and at the Earth rotation pole, you don't expect to see the splitting. I mentioned previously that the magnitude of the earthquake was first estimated at 9.0. It's now been revised upwards by several studies, in particular through the analysis of the amplitudes of these very grave modes, which, if you project back these amplitudes to infinity, you basically end up with a measure of this moment of this earthquake, which in fact corresponds to a magnitude of 9.3. Another aspect of analysis of these data is to look at the attenuation of the modes as a function of time. And the mode 0S0, this mode which corresponds to the radial vibration, is particularly interesting because it vibrates for many, many days. In fact, a month after the earthquake, we can still pick it up. We could still pick it up here on our Berkeley seismographs. In fact, it's picked up in a strange fashion. We have a software that allows us to monitor the noise on our stations, and this noise around the period of the 0S0 mode was picked up very systematically. And of course, looking at it, we were able to determine that it's just the 0S0 mode continuing to vibrate from this earthquake. But the information on the decay of this mode it can be used to constrain the not only to constrain the bulk attenuation of the global Earth, which is a parameter that has not been very well constrained so far.
So now, to finish, let me just move on to this was just an example, a spectacular example of a recent earthquake, which happened just at the right time for seismologists, because they were ready in terms of the distribution and quality of their recordings around the world. But one large earthquake is not enough to learn everything about the interior of the Earth. And in fact, what we really do to study the Earth's interior is to combine the information from many earthquakes. So again, this is just a standard seismogram with the so-called body waves that travel through the Earth, the primary waves, the secondary wave, and then the surface waves. And again, they travel through the Earth, they interact. And so by combining data from many earthquake sources around the world, and this is just 20 years of data, the coverage would be much larger if we used another 10 years of data, and then all the stations that populate the Earth. And we can apply methods that are very similar or related to methods that are applied in medical tomography, where instead of determining the difference in density of various matters inside the Earth, the human body, you will pick up differences in velocities as the waves go faster and slower in traveling through different parts of the Earth. So we are able to map the regions that are faster and that are slower, and we use this in a first approximation as proxy for temperature. The main effect that speeds up or slows down the seismic waves are the temperature differences. So if you have a rising current, current in a global convection system, it will be both lighter, less dense, and hotter, and so it will tend to appear as red or slower velocities. On the other hand, if you have a subduction zone or a zone of downwelling, which is cold, you will tend to see blue regions. And so that's and the principle of tomography is, of course, if you have a homogeneous body and you measure the travel times of waves across different sources to receivers or to stations, you will find no difference with respect to your reference model for this body. But if you introduce some heterogeneity, if you only have one pass, then you will know that there is some heterogeneity that is sampled by this one pass, and you need many other passes to kind of constrain the shape and the strength of this anomaly. And of course, if you have many other anomalies, you need to combine all this information and process it to obtain an image. So back to the standard model, this is of course only a sketch. The actual motions of matter inside the Earth are not as simple, except perhaps that we're fairly sure that in subduction zones material goes down. This is manifested not only by the tomographic images that I'll show a little bit of, but also there is seismicity that accompanies the downgoing of these so-called slabs down to at least 700 kilometers of depth, or to 700 kilometers of depth. So what are the main sort of issues that seismologists and more generally geoscientists, global geoscientists are trying to get at? There's a lot of debate. There's now 40 years after establishing the plate tectonics theory, we still don't really know how it works, and there are competing models. We don't know whether the Earth's interior is, or the Earth's mantle has two separate layers, an upper mantle and a lower mantle that do not communicate with each other. We know that there is an upper mantle and lower mantle because we can track by seismic investigations that there is a discontinuity in structure at about 700 kilometers depth, 660 more precisely. What is the communication between the upper and the lower mantle? These are the big questions that are still being answered. Some like to see two completely separate reservoirs. Some like to see some communication both downward and upward, but limited to some particular areas of the Earth. Some models show a blobby Earth with a sort of complex mixing, and some others have this concept of some boundary layer at the bottom of the mantle, from which would be like the graveyard of slabs, and from which large upwellings and so-called plumes would be. And so seismic tomography and seismic investigation in general are our best approach to try and figure this out. And so far, we have some ideas, but the images need to be made more accurate, which is one of the challenges that we face right now. This is some examples of cross-sections of models through subduction zone areas, so areas where one plate goes under the other. These are vertical cross-sections, so this is depth, and this is along the surface of the Earth. And you can see these blue regions here that you can track as corresponding to these slabs going down into the mantle, these cold slabs. Some of them seem to go straight through, some of them seem to stagnate at this 660 kilometer discontinuity. So these images, which is sort of still represent more or less the state of the art, seem to indicate that we do have some connections, between the upper and the lower mantle, but that this connection does not necessarily occur instantly, or that it shows some complexity. Other types of models, which use different types of seismic waves, come up with a global distribution of mapping of structure. These are comparisons of 4 models, one of which is one of ours here at Berkeley, showing, these are now slices, horizontal slices in depth, and showing in the upper mantle, you see these red zones, hot zones, slow zones correspond to the ocean ridge system and the back arc regions in the back of subduction zones, whereas the fast regions or cold regions correspond to the old shields on the continents. This tectonic distribution has very good correspondence with what we see in seismic tomography in the first 200 kilometers, and you start losing it by the time you get to the mid-mantle. The mid-mantle looks much more blander. This is the zone which is now the focus of a lot of attention to try and extract the details of the structure. And by the time you get to the Commando Boundary, you see again some very striking large-scale features with 2 slow regions under the Pacific and under Africa, and a ring of high velocities around the Pacific. And if you look at those, I'll skip this, a little bit in more detail, you see going from the Commando Boundary here at 2,800 kilometers up into the mantle, you see this structure, very, very striking structure at the bottom, which is now rises into the mantle, but becomes much more narrow. And in cross-section, this is, you can see, we see these, we call these super plumes, and we think they are upwellings rising from the Commando Boundary. We don't really know what the detailed structure of them is. There is a strong debate as to whether they're really very large scale like this, or made up of a large number of narrow so-called plumes, and this is what we're trying to figure out these days. This is another picture of the Pacific, so-called Pacific superplume, which shows this slow anomaly, quote-unquote, rising into the mantle, and also continued in the upper mantle by corresponding heterogeneity. So these features are the most intriguing. In addition to the subduction zones in the upper mantle, these low velocity structures at the bottom of the mantle are very intriguing. There is now evidence that they have very sharp boundaries that you can pick up by looking at detailed waveforms of seismic waves.
And the sharp boundaries with very large contrasts in velocity cannot be explained only by temperature. So some compositional heterogeneity must be present to build these very large structures. And so to finish, I just want to conclude by just giving an idea of the current directions in my field. They are basically in two directions. One is improve the global distribution of stations, because I showed you this map with a large number of stations around the world. What I didn't point out is that there are still gaps, and the gaps are in the oceans. The Earth is covered 2/3 by oceans, and so to get a really good view of the Earth, you would need to have stations on the ocean floor. But putting stations on the ocean floor is a technological and financial challenge. We've been working on it for 20 years, since 1985, trying to establish a program of maybe 20 stations on the ocean floor to fill the main gaps in the distribution. And that is still not done. There are some pilot experiments, stations that operate for maybe 6 months to a year, that provide useful data. We know how to solve the problem, but just the sheer expense and logistics of development has really thwarted this. But it is really something we need to make progress on understanding, in particular, what happens under the oceans, which are less well covered than the continents on which we have stations. And then the other aspect of this is the more modeling aspect, which is that the current models rely on very simple assumptions on how the waves interact with the structure. Now we are in a position, because of progress in the theory and computational capabilities, to implement very powerful codes that can model the seismic wave field in great detail for any type of three-dimensional structure, whether it's weak or strong. And so implementing these types of computational scheme is something that is in the works, and will likely bring a lot of exciting new details in our ability to map or to image the interior of the Earth in the next few years. So thank you.
Good.